In this series of machine learning videos, today I'll be diving deep into the basics of linear regression. This is my first video in this series. Okay, so let's start. So by linear regression, what do we exactly mean? So by linear regression, we mean that we want to predict a y variable given some x variables. So these x variables are the feature variables and the y variable is the target variable. And linear means that y can be expressed as a linear combination of the x variables. Okay, so now I'll be talking about an example dataset and I'll show you how we can plot the points, because whenever we deal with any machine learning problem, the first thing is to plot the points. So first thing that comes is what kind of dataset are we looking at? So this is an example dataset. So this x is the feature. This y is the target. So the first thing that we need to do is plot the points. I'll talk about how to plot points using coding, using standard softwares and all when I talk about the hands-on coding videos. But now I'm going to just do it manually. This would be an approximate line that actually satisfies all the points. These differences, these are the losses. These differences are the losses, basically. So our goal is to find the equation of this line. So this line's equation would be y equal to ax plus b, and we want to find a and b. So basically this line is also called the best fit line. Okay, so now next comes this a. This a is also called, like in our geometry lessons, we have learned the equation of the line. And here a is basically the slope as we have learned, and b is the intercept. In ML terms, A is going to be the weight and B is going to be the bias. A is going to be the weight and B is going to be the bias. And this is the equation of the line that we are looking for. Okay. Great. Now the next thing that comes into the picture is how do we find the equation of this line? So first thing we need to do is basically get the loss. So what does the loss mean? So as I drew this line, you remember I was saying that these differences are the losses. So we want to find an equation for these differences, and then our target would be to minimize the loss so that we can find the equation of this line. So the first thing that comes into play is initializing these weights. So I'm initializing with 0, 0. You can also initialize it with random values. So after you have initialized these values, then the next step that comes is getting a function for the loss. So this loss would be somewhat like we have to take into consideration, intuitively we have to take into consideration all the points. So let's say we have m data points in our data set. When I showed that, it was m equal 3, but obviously we would have much more. So m data points we have, and we have to account for all the data points while writing the loss. Now the loss, there are many functions of losses, but we are going to look for the least squares loss function. That is the most common loss function. Okay, so this is the function of the loss function. M total number of data points, 1 by 2m summation I equal 1 to m yi minus axi plus b squared. So this is the least squares loss function. This yi is the target value which we have in our data set, and this is the predicted y value. As I said, our equation, this yi would be the predicted one which we get by placing 2 in this equation, but the actual value is 11. So this is the loss, and we are squaring it out and then taking all the summation, and our target is to minimize this loss so that we can get this line that is closest to all the points. And so what is the purpose of this line? Once we have this line, regardless of whatever value of x we have, we can get the value of y without any effort. We just need to put the value of x in this equation and we'll get the value. We can predict the value easily. Okay, so now what comes is that plotting this loss function. So now this is a least squares loss function. So this would be the plot of the loss function. We are currently at this stage which is the starting loss. It would be obviously high. We can't be at the minimum at the start. So this is the minimum loss. And our purpose is by each iteration, slowly, we want to get to this point. We want to get to the minimum loss. So this is what is called the gradient descent. Because we are descending along the gradient. So this is our target basically. Okay. So this loss function, what is it a function of? So it's a function of A and B. So this loss function can be said to be a function of A and B. JAB. And our target is to minimize this loss function. So that is our next thing that we'll do. Okay. So how do we plan to minimize the loss function? We have learned in calculus that the best way to minimize any kind of function is to differentiate it and to equate a differentiated function to 0. Obviously, we can't equate it to 0 here, but we'll try to get it as close to 0 as possible, slowly, step by step. So let me write it down. J is a function of AB would be 1 by 2m summation I equal 1 to m yi minus axi plus b squared. So you see here, this is yi minus axi plus b squared 1 upon 2m. So next thing what we want to do is to differentiate this j with respect to a. We'll differentiate this j with respect to b and then we'll try to get them down to 0 as much as possible. So what would that look like? You also, I would suggest using pen and paper, and as I'm doing it, you also do it on your own and try to match the answer as you go. Comes down minus xi. This is the dj with respect to dA, and dj with respect to dB would be yes. So now we have dj with respect to dA and dj with respect to dB. Match your answer and see if you have done it correct, if you remember your calculus basics or not. Or it might be a little bit time to actually go over differentiation, integration, and so on. Integration not that much, but differentiation we'll need. So these are the two values that we have with us right now, and we want to get these down to 0. So what is the way to do that? So, okay, so remember these functions. I remembered them. You need to remember them because that is what is asked in most interviews. And it's a variation of these types of things. And if you're able to explain this properly and clearly, then the job is yours. Okay. So now, before we start, we have A1 equals 0 and not A2, but we have A1 equals 0. As I said, we are initializing with 0, 0. A1 equals 0 and B1 equals 0. So the next step, what we'll do is A2 would be equal to A1 minus gamma, which is a constant. And this constant is actually called learning rate in machine learning. So J, A comma B with respect to dA and take the value of A1. And B2 is B1 minus gamma djAB with respect to dB at the value of B1. So this is what we'll do slowly, step by step, as I showed there. Here we are, slowly, step by step. So this one would be J A2 comma B2. This is J A1 comma B1. And this, whenever we get near this, it would be J A final comma B final. And this is what we're looking for, A final, B final. Once we have the A final, B final, we would be able to construct this A final X plus B final. And that is our line. Then we can just put in any value of X. Our test variables would be putting in any value of X and we would be getting the Y value, which is our target. So this is what we need to do. So at each iteration, what we will do is we'll get the new value of A2 and B2. while putting in the value of A1 and B1 in here. So that we will do. So I can write it in a better way. So suppose this is J. So let's just say, or maybe it's K, whatever. This is AK and this is BK, AK, BK, and then this would not be 2 then. Just like just generalizing, this would be K plus 1, BK plus 1. So now we have AK plus 1, BK plus 1 in terms of this, and we are able to get the new variables. So as soon as we have the new variables, the next step is to basically do this thing until, now this is very important. What is the stopping condition? You can't do this forever. So you will have to see, you will have to check. We will do this until the cost function does not change by much. So until AK plus 1, comma, BK plus 1 is the J. Remember, J is the loss function. So the losses are not differing by much. So what is much? So J, AK, comma, BK less than 10 to the power minus 6. As soon as this becomes less than 10 to the power minus 6, we are done. This is the threshold. We just need to go below this threshold and then we are done. So this equation, you need to write it out. I'll also write it out. You can write it out on your own. Memorize that. Remember that. In interviews, it's very important. You get it in terms of you get it in terms of MCQ, you get it in terms of any other thing, like whatever things you actually appear for in questions in jobs and all. Interviews, they ask you. In online assessments, they ask you and everything. So remember these. I remember them and I'll just write these two equations in complete form after putting in these values. So what would this look like? A1 minus gamma minus 1 upon m summation I equal 1 to m yi minus axi plus b multiplied with xi. So this you can just simplify it doing plus and the rest stays the same. This is for A. For B you can do it, but I'll still just do it in case you want to match the answers. Yes. So now I think you can do it on your own. B2 equal to B1 minus gamma times this. So you can just place it there, and this is the final equation. So I'll just do this one. So this is the final equation that you need to remember, and this will come in use in your interviews. So after you do this, till the step that I said, until and unless the difference in loss is less than 10 to the power minus 6, which is the threshold, then whenever that is true, then you can just stop it. And that will be the final A final value, B final value, final weight, final bias. And you have the equation as y equal to A final x plus B final. Yeah, so that's the final thing. Today I'll be talking about the derivation and maths behind multiple linear regression, which is the second algorithm in this series. I've already covered simple linear regression before in one of my videos, and so today it's going to get a little bit more involved. So without any further ado, let's start. So the first thing that comes is, what is the dataset? So the dataset looks something like this. We'll have like around n features, and we'll have m data points. So these all xi's, x1, x2, x3, xn, these are all n features. And y is our target variable. So total we have m data points. So this is very important to understand. Total we have m data points. And we have n features. Total we have m data points and n features. So our x matrix, so we know that we are given x, we try to find y. So our x matrix will be m cross n. M being the number of data points and n being the number of features. And y is m cross 1, as we know, just a single value. This is y and this is x. Okay, so now we have the data set. We understand what the data set looks like. Okay,
So now we have the data set. Now we want to find out the curve. What curve will satisfy our multiple linear regression problem? So basically, in simple linear regression, we know that since we have one x and one y, and it's linear, so y would be mx plus c or ax plus b, some linear function of x. So now, in case of multiple linear regression, we'll be having like x1, x2, xn, n features. So y would be a linear combination of these n features along with a bias. Okay, so what does it look like? Y would be theta 1 x1, theta 2 x2, theta n xn plus theta 0, which is our bias. We cannot use A, B, C right now here because otherwise it will be difficult to formulate the expression and the loss. So remember this is the curve. So let's visualize it. It's very difficult to understand without visualization. So let's visualize it. So wait. So suppose we have just two. We already saw what it looks like when it's only one. So y equal ax plus b. This would be a line. Y equal mx plus c or ax plus b. Now, if it's multiple, suppose we have x1 and x2. Suppose we have x1 and x2, right? And we have y. So y would be theta 1 x1 plus theta 2 x2 plus theta 0. So now let's denote this as x, this as y, and this as z according to the axis. So I'll explain what I'm trying to say. So suppose this is x, and okay, this is not x. Yeah, suppose this is y, this is x. So x cross y would be z. Z is in this direction, x is in this direction, y is in this direction. And we know the curl formula. So x cross y is z. So this is z. Now, suppose we have some theta 1 x1 plus theta 2 x2, and then some constant. So we have some kind of here. This is the target. And so therefore the curve would be something like this. A plane. This would be the curve. Satisfying all these points. When you just project it down, it will be in terms of x and y. And it is like a 2D curve, which is a plane. This is a plane. So now we are trying to find the equation of this plane, which is the equation of y equal theta 1 x1 plus theta 2 x2 plus theta 0, which is our target right now. Okay, so now comes the loss. So we need to define losses first. So in simple linear regression, if you remember, if you have seen my video, and if you have even seen some other videos and you know what is simple linear regression, then you probably know that this is the line and these are the points. This is the best fit line or the best fit curve for simple linear regression, and the differences are the losses. So the loss would something look like, the loss is the least squares loss function, which looks something like the sum of these differences squared. So this is the least squares loss function. So similarly, we would have something like this in multiple linear regression as well. So what would that look like? So that would be something like this. Suppose we have yi, which is the target. Y is the target, which is in our data set. And we are predicting y pred I, which is our predicted value. So we know that yi minus y predicted I, this is our loss. And we are using the least squares loss function. So y predicted I, so that you just now saw theta 1 x1 I plus theta 2 x2 I plus theta 0, right? So this is my y predicted value. Now there's an interesting way to write this. So we want to write it in the form of a vector so that we have simple equations to solve instead of this complicated equation with all the variables. So now, okay, so now theta. How do we represent theta? So theta would be n plus 1, right? Total number of thetas will be n plus 1. Those theta 0 to theta n for each of these x1 to xn feature. So theta matrix would be theta 0, theta 1 till theta n. 1 n plus 1 cross 1. This is our theta matrix. And our x matrix looks like this. I already said m cross n. Right? M being the number of data points and n being the number of features. So now our y would be m cross 1. So now if you can see carefully, so theta 0 has 1. This is very important. Try to understand this. This is the trick that you will use in most of the algorithms when you are trying to find the and solve using the vector formula. So this is the 1 that we have. So let's say if we had x0, it would have been 1. So what we'll do is we'll add a column here of 1s. So then we'll make this. Let's make this. So this would be, these are the n features we have. Now we'll have another column of 1s. So this becomes plus 1. So this becomes n plus 1. So now you can see this is m cross 1, this is m cross n plus 1, this is n plus 1 cross 1. So we have a matrix multiplication here. So if we have theta transpose, what would theta transpose be like? 1 cross n plus 1. And then we'll have x. So we can write x in the form of like n plus 1 cross m as well. So that just depends on how you express x. Let's do that. Suppose we want to write x in the form of n plus 1 cross m. N plus 1 cross m. So this is our final x coordinates. So this would be n plus 1 cross m. Now we have 1 cross m, which is our y. So we can say y transpose, or we can represent it in the same way as x. So in that case, y would be 1 cross m. So it doesn't really matter when you're trying to solve. This is just the way we choose to express this formula, and we choose to relate y and x and theta. So this would be 1 cross m. So now you have this 1 cross m. So you have this equation, which is like very common, y equals theta transpose x. Now we want to use this. Till here, I think it's all clear. Now comes the loss. So we use J in order to represent our loss. So this is the I equal 1 to m, 1 upon 2m summation yi minus theta transpose xi square. So this is our least squares loss function. So I said this is our y predicted value, this is our y target value, and this is the way we represent the least squares function. So now we have the loss. So now we know what to do. We want to minimize this loss. So randomize, start, like initialize theta with some random values or 0, whatever you want. And then differentiate this loss function with respect to theta to get an equation, and then equate it to 0. And then not equate it to 0, step by step, bring it closer to 0. Like normally we do in gradient descent. Okay, so but I'll still explain it in case you're new here. Okay. Okay, so the next step is differentiating this with and equating it to 0. So what does this do? So suppose this is our curve. For simple linear regression, this is what the curve looks like. So here we are currently, this is our j theta. So this is our currently the loss function which we have after putting in 0 or any kind of random value. We are starting here. Now, since this is the slope, so we move along the slope slowly, and we try to reach this point, which is our target. Since what is this? This is the minimum loss. We want to reach this point. So what are we going to do? Simple, just differentiate this with respect to theta. I'll write the expression. Try it yourself as well and then try to match it. Okay, so one thing to clarify, this is for simple linear regression, but this can be extended to multiple linear regression as well. But trying to understand this by visually, this is very important. This is the curve, and the purpose is like the same. It's just extended to the multiple linear regression as well. The curve would not be exactly similar, but it would be same, almost similar. Okay, just one small tip here before we move on. Remember this, that when you are trying to solve a hard problem, it's always better to solve the easiest version of the problem and then step by step build it towards the hard problem. So here, multiple linear regression is relatively tougher compared to simple linear regression. But if you have learned simple linear regression already, and then multiple linear regression will be a piece of cake. It's very easy because it's just an extension with a little bit of vector formula and a little bit of more equations and a little bit more imagination and visualization. So if you have that out of the way, simple linear regression, then you know that multiple linear regression is nothing. So that is why do not try to jump directly into hard topics. Try to break them down. If you have suppose a hard problem in interview or in exam, in any case, then try to find out the easiest version of the problem. Put some constraints. Try to think of in a perspective you can visualize and then solve it. And then you'll see that the harder problem becomes very easy and you have a path. Okay, enough pep talk. Let's continue. Let's finish this. Okay, so now we use the gradient descent formula. This is theta, t plus 1, t being the number, tth step, minus theta, not d, but delta, since we have multiple dimensions. D theta. So this is the gradient descent formula. This is our constant. We need a constant to determine the rate of convergence when we're trying to, as I said here, when we're trying to go from here to here. The rate of convergence is dependent on this learning rate. Now we are going to break this down. This is our, this is the toughest looking thing in this formula. Okay, so what is this and why is it creating problems in our life? Theta 0 upon d 0, d theta 0, d theta j1 upon d theta 2, d j theta n upon d theta n. This is our derivative. Now we are going to break this down. We are trying to find out. Let's try to find this out. So it's better not to do here. We won't be able to finish. So let's remove this. So now what we have is theta j d theta j. What would this look like? So if you remember, just I'm trying to write this here. Let's write it here. I'll remove this summation 1 upon 2m I equal 1 to m yi minus theta transpose xi square. This is what we are trying to differentiate with respect to theta j. So theta we know we have n thetas, n plus 1 thetas, theta 0 to theta n. M is a number of data points. Yi is our target. This is our predicted value. Okay. And the light falls here, but if you can see here, d theta j upon d theta j. D j theta j upon d theta j. Okay. So let's do that. Theta j. Y upon theta transpose xi square. This is 1 by 2m. So it's just a constant, so we can take that out and put it here. This is what we need currently. If it is not clear, 1 upon 2m. Yeah, now it's clear. So we have d theta j, and then we have summation I equal 1 to m yi minus theta transpose xi square. Now let's differentiate. So this is partial differentiation. Remember this. We have here all the thetas from 0 to n. So this is partial differentiation. So if you feel a little shaky here, just remember that what happens in partial differentiation, we keep all the other terms constant except theta j, and we differentiate with respect to theta j. So this is just a simple funda of partial differentiation. Great. Now let's do that. And now this one. So minus, the others are all constants, so they'll all be 0. Only theta j will remain. So what is it? Minus theta j xi. So minus xi. That's it. Done. This is our differentiated value. If this xi, remember that when I was doing when I changed x, which was m cross n, into m cross n plus 1, I added a series of 1s. So Just remember that in the case of theta 0, it will be 1, minus 1. That's it. That's it. Literally, you have done it. So now we are done. Just remember this 1 upon m summation I equal 1 to m yi minus theta transpose xi minus xi. This is the formula that you need to remember, and we are done. And this has to continue until, we know that this is continuing until, and so this will continue until we have j theta minus, let's say theta plus 1 minus j theta t, like mod, absolute difference. This is less than 10 to the power minus 6. So basically, what do I mean by this? Whenever this happens, the difference in the losses or the cost function, whatever you say it, whatever you call it, this is less than, like very less. It's not changing by much. So we know that we have reached our training is stable, and we have reached convergence, because it's not changing by much. It's not going to change now anymore. This is just a value we generally use for threshold. This can be any threshold that you want. This can be any threshold that you want. Okay, so now, so the curve looks like something like this. Here we are starting out. Here we have some value. Let's say we have some loss, and the loss is continuing to decrease. As you can see here, the losses are very small, and here it's almost negligible. So 10 to the power minus 6 is like a threshold that we generally use. You can use 10 to the power minus 9 if you want more precision, but that's up to you. Exactly is log likelihood, and why do we need that? So first, let's come to likelihood. So likelihood of a data is actually a quantity that is often used to compare different models. So what do we mean by that? So we have something called a likelihood of the data given the model. I know it sounds crazy, but suppose we already have a model and we want a particular data to fit the model. We want to see whether the data is actually in line with the model or not. That is, the distribution of the data fits the model or not. What we often do is, like, we have a data and we try to see whether the model fits the data or not. We try to find a model that fits the data. But here what we are doing is that, what is the likelihood of the data given the model? What is the likelihood that the data is generated using the model? So that is what is the likelihood. And we often, obviously, we want that the likelihood of the data given the model should be maximum. So I mean, if a model actually fits the data, then the probability of the more data being generated from the model has to be maximum, and that only proves that the model is actually that the data is actually produced by the model, and the model fits the data. So that is a different way to think of it, and this is a very important quantity that is often used to compare different models that are trained by different algorithms. So let's consider an example. Okay, so these are two lines. Suppose this is an L2, which is a linear regression, which is a linear regression line that fits a particular type of data, and L1 is another linear regression line that fits a different kind of data. Okay, so if we're trying to use L1 to fit a data that follows the distribution of L2, then the likelihood of the data of L2 being generated by L1 will be very less. Obviously, I mean, suppose the data, like, let's consider the data is something like this, and the other data is something like this. So this data, let's call it D2, and this data, let's call it D1. So if you remember my linear regression lecture where I talked about the how we find the regression line and how we use the regression line to fit the data. So here is similar. So this data D2 is being fit by L2, and this data D1 is being fit by L1. So now, if suppose we have a data which is D2 and we have a model which is L1, then the likelihood of the data D2 being generated by L1 is almost zero, because they are almost perpendicular. So it's impossible. Similarly, the data D1 being generated by the model L2 is also, the likelihood is also zero. So we want to maximize the likelihood. So likelihood of the data D1 being generated by L1 is maximum,
And the data of D2 being generated by L2 is also maximum here. So that is our main target. And likelihood we often use likelihood when comparing different models. Okay, so now comes how do we want to express the likelihood mathematically? Okay, so for this, what we'll need is L theta is often used to denote likelihood function. Let's break this down. So P means probability of yi. Yi is the target variable, and xi is the input variable. All the features that we have, and parameterized by theta. What is theta? Theta is the weight. So in linear regression, you know that we have. This is what we have, right? In linear regression, we try to fit. This is the predicted value. So we have some noise. Definitely. And this noise can be distributed in any way. And yi is the value, is the target value that we have when doing the linear regression. If you remember this part. Yeah. And theta is the weight for the model. And this xi is the feature of all the data points. So m is the number of data points. So remember this formula. This is the mathematical quantity that we use to denote likelihood. Okay, so now let's give an example. Let's try to model this noise as something which is generated by Gaussian distribution. I'll explain the Gaussian distribution if you don't know. Okay, so first I'll go over the Gaussian distribution. So let's refresh our memories. Gaussian distribution, right? So so what exactly is Gaussian distribution? So if you remember, so this is a kind of like distribution where we try to generate data based on a particular probability. So this is the Gaussian curve. And okay, so how does the Gaussian distribution look like? So the formula for that, like PDF, is 1 upon root over 2 pi sigma square e to the power minus half x minus mu square upon sigma square. Right? So I'll go into it in detail. So this sigma is the standard deviation. Sigma is standard deviation, and mu is the mean of this distribution. So in this case, here we would have the mean, and this would be the standard deviation. So this is how the Gaussian distribution looks like. So we want our noise to be generated by the Gaussian distribution. And then you will see some brilliant results, actually, which will prove that why we use the maximum likelihood in place of minimum loss. So if you remember in linear regression, I talked about that. I said that we were using minimum loss. We were trying to find the function for the loss and then try to minimize that. But in all next consequent videos, what I'll do is in all kind of models, what we'll do is try to minimize the loss by maximizing the likelihood. So we'll see why maximum likelihood means minimum loss. Okay. So remember this now. What we'll do is now we will try to model the noise as in the form of this Gaussian distribution. So if you remember, just now I wrote a formula, this one, and this is the noise. So we want the noise to be generated by Gaussian distribution. So what would that look like? So that would be like beta transpose xi. So this is the noise. This is the probability distribution function of the noise. So let's just consider sigma, and sigma doesn't have a meaning here. I mean, we know what it means in normal Gaussian distribution, but here it doesn't have a specific meaning. We can treat it as like a general constant. So now we'll see the magic happening. So this, if you remember this one, try to remember this. So now what we'll do is something different. So this function that you have right here is this noise, right? This noise is this function that you have right here. So now we will, so and if you remember this one, this is actually the one that we wrote like right now, the function for likelihood. So now I will use log likelihood.
Why?
It's easier to like differentiate when it's in the log format, and also the variables, they are more easy to deal with. So P. So this one would be P probability of yi given xi parameterized by theta. I just now said this one. Right, this one. And this would be for all the data points. M is a number of data points. Now we will take the log of this. Log on both sides. So what would that look like? Summation I equal 1 to m log of 1 over 5 6 square plus summation I equal 1 to m log of to the power minus of y square. This is what it would look like, right? So now this is just a constant, so we won't take it any further. And this one is actually what matters. Constants we can deal with later because we are anyway minimizing the loss or maximizing the likelihood. So it doesn't really matter. Yeah, so this one, then log comes this. Let's take it down. You will soon see that it looks very familiar. See this. What does this look like? The least squares function. Exactly, correct. If you got it, then great. This is basically, now we're trying to, this is basically the log likelihood function. And this is what we'll try to maximize. Why? Because if you see the minus sign, if you try to maximize this, this is the loss. This is the loss. And this is we're trying to minimize, which means maximizing the likelihood, log likelihood. That's it. So you see the linear regression loss, we get it from here, even though it was like, it seemed that it would not be possible. That is why like likelihood so much matters in our daily lives. Like in all models, you will see that you will always try to get to the maximum log likelihood. In future functions, this is just a quantity that is easier to deal with. I'll also show in future videos in naive Bayes and in other algorithm classification algorithms, you will see that this is what matters the most. I'll be discussing the derivation and maths behind classification, which is another top ML algorithm. I have covered log likelihood before in this video, and I would say it's kind of a prerequisite for this video. If you already know about that, then without any further ado, let's start. So the first thing that comes is, what is the problem that we are trying to tackle here? So basically the first question always is, what's the data set? What does the data set look like? So it looks something like this. As I said, we'll start with the simplest form first. So x1, x2, and y. So y is basically either 0 or 1. We'll be tackling binary classification first. So y is either 0 or 1. Let's say it looks something like this. And x1 could be 1, 2, 3, 4 maybe. And x2 could be anything. 0.5, 0.9, 1.0, 1.1, anything. So these x1, x2 are the two features, and y is our target variable, which is either 0 or 1, and we want to predict y given x1 and x2. So now comes the graph. Exactly what are we trying to find here? So we'll try to plot x1, x2 here, x1 and x2, and then we'll try to get the points here. So let's just say these are the 4 points that we have. So now what we're trying to find is this line, because this line would be distinguishing these points. Suppose this point has y equal to 1, and this point has y equal 1, this point has y equal 0, this point has y equal 0. So this is the line that we're trying to find, that
differentiates the y equal 1 from y equal 0. Because suppose now we have any kind of point, suppose x1 is here something and we have given x1 and x2 and we find it here, then we know that this point lies on this side of the line, so y will be 1. It's as simple as that. I hope you get this. So basically x1 and x2, given x1 and x2, what is our y? That is our target to find. Given x1 and x2, we want to find y. Fun fact. So logistic regression is also called classification. Do you know why? Drop your thoughts in the comments. Okay, coming back to this one. So this line in classification is called decision boundary, which is very important. Remember this term. So what is the definition of this line? This line is the maximum distance from all of the points. So what do I mean by that? So here actually we are tracking the distance between the points. So these differences, this is the di. For each point x1i and x2i, we have this point which is di, and this di we want to maximize because we want the line such that it differentiates the two 1 and 0 completely. Okay. So what is exactly the equation that we're trying to solve here? So yi given xi parameterized by theta. This is the equation that we're trying to find. Why are we trying to find that? Because if you remember correctly, this is log of this summation I equal 1 to m being the total number of data points. M being the total number of data points. So this equation is the log likelihood. So this is very important. So that is why we are trying to find this and we are trying to define this term. So this is actually yi given xi parameterized by theta. This is actually the Bernoulli distribution. Because either the probability, we are trying to kind of find the probability of it being 1 or 0. And Bernoulli means only two values we can predict, 1 or 0. So that is why this is like similar to the Bernoulli distribution. Now that we have got this out of the way, we know what we are trying to find. So now comes the di. Let's focus on di. Let's get an equation for finding out di and formalizing that. So if you remember, I just now said these are all di. So this line, this side is a positive side of the line and this side is a negative side of the line. So we can either decide we can decide the direction. So let's just say this side of the line is positive and this side of the line is negative. And then this di, let's denote z as di. So now this is very important to understand. So listen carefully. So this di, it can range from positive infinity to minus infinity. So we are trying to find a function. So di can range from positive infinity to negative infinity. Okay, so now if di is 0, let's say for a point, the point is lying on the line. So we don't know whether it's positive or negative, whether it's 1 or 0. Let's just say positive 1 gets classified as 1, negative is classified as 0. So if the point is on the line, we don't know whether it's positive or negative. We don't know whether it's 1 or 0. So the probability is half. So di equals 0 should have the probability as half. We are now trying to find the constraints for finding the function that will fit di perfectly. So di is 0, p is equal to half. What if di is positive infinity? Which means that probability will be 1. And then di, suppose it's negative infinity, then probability will be 0 of getting classified as 1. So we are finding that we are now currently thinking of p as the probability of getting classified as 1, this one. So if it's on the line, then it's 0, then probability is half. If it's infinity, which means we know for sure that it's 1. Point is 1, so p is equal to 1. And if it's negative infinity, we know for sure that the point can never be 1, so its p is 0. So now what function fits all these conditions? Yes, so that is the sigmoid function. Write this down. This is the sigmoid function. So what does this look like? So now we are going to see how the sigmoid function looks like. We denote it generally as g as a function of z. It would be 1 upon 1 plus e to the power minus z. This is a sigmoid function. So let's put in the values and see if it satisfies it or not, as we just now saw. So if z equals 0, then what is gz? It is half. Perfect. If z is infinity, what is gz? Gz is 1. Perfect. Because 1 by 1 plus e to the power minus infinity, this would tend to 0. So we have 1. And if z is minus infinity, then gz is equal to 0. Why? Because 1 by 1 plus e to the power infinity, this tends to infinity. So 1 by infinity is 0. So now we have a function which satisfies all these points. So now we have our ideal function. So sigmoid function is what we are going to use here. Before I delete this, let's see the curve of the sigmoid function. So this is 1, this is 0, this is half. So at half we have at 0, z equal to 0. So this is z, this is gz. So when z equal to 0, then we have half. When z equal to infinity, we have 1. And when z equal to minus infinity, we have 0. So somewhat like this. This is the sigmoid curve. Remember, this is very important, comes in interviews, comes in placements, wherever, jobs, internships. This is extremely important. College exams, gate exams, whatever. So this is very important. So now we have the sigmoid function out of our way. Great, one down. So now we'll find out the log likelihood. So probability of yi equal to 1 given xi parameterized by theta. Probability of yi equal 1 given xi parameterized by theta. Earlier it was probability of yi given xi parameterized by theta because yi was continuous. In distinct case, it's a little bit different. So we'll take yi equal 1 and we'll take yi equal 0 and we'll get the formula for these two. Then we'll see what to do, how to combine them together. That's very interesting as well. We'll come to that. So this is the yi equal 1 given xi parameterized by theta. So we just now found this 1 plus e to the power minus. So now what is this term? What is this term? So basically, if you remember, when I was talking about the decision boundary, in binary classification, it's going to be a straight line. Obviously, because we are trying to divide these points, this distance we are trying to maximize. This distance we're trying to maximize from all the points. So this is a straight line. So now we know what is the function, which is the equation of a straight line. It's y equal to mx plus c. But this is only when it has only one feature, which is x. So we have here two features. So then what are we going to do? So this is going to be y equal to theta 1 x1 plus theta 2 x2 plus theta 0. So we have x1 and x2 as I showed earlier in our data set. And so we will use this equation. So basically, what does this equation mean? And how can we write this equation? So I'll just play a short video here where I've talked about how we can get this equation and write it in the form of y equal theta transpose x. So here it starts. It's just a few seconds video. So yeah, so you'll understand why we are writing y equal theta transpose x from this equation. Now there's an interesting way to write this. So we want to write it in the form of a vector so that we have simple equations to solve instead of this complicated equation with all the variables. So now theta. How do we represent theta? So theta would be n plus 1, right? Total number of thetas will be n plus 1. Those theta 0 to theta n for each of these x1 to xn feature. So theta matrix would be theta 0, theta 1 till theta n. N plus 1 cross 1. This is our theta matrix. And our x matrix looks like this. I already said m cross n. Right? M being the number of data points and n being the number of features. So now our y would be m cross 1. So now if you can see carefully, so theta 0 has 1. This is very important. Try to understand this. This is the trick that you will use in most of the algorithms when you're trying to find the and solve using the vector formula. So this is the one that we have. So let's say if we had x0, it would have been 1. So what we'll do is we'll add a column here of 1s. So then we'll make this. Let's make this. So this would be, these are the n features we have. Now we'll have another column of 1s. So this becomes plus 1. So this becomes n plus 1. So now you can see this is m cross 1, this is m cross n plus 1, this is n plus 1 cross 1. So we have a matrix multiplication here. So if we have theta transpose, what would theta transpose be like? 1 cross n plus 1. And then we'll have x. So we can write x in the form of like n plus 1 cross m as well. So that just depends on how you express x. Let's do that. Suppose we want to write x in the form of n plus 1 cross m. N plus 1 cross m. So this is our final x coordinates. So this would be n plus 1 cross m. Now we have 1 cross m, which is our y. So we can say y transpose, or we can represent it in the same way as x. So in that case, y would be 1 cross m. So it doesn't really matter when you're trying to solve. This is just the way we choose to express this formula, and we choose to relate y and x and theta. So this would be 1 cross m. So now you have this 1 cross m. So you have this equation, which is like very common, y equals theta transpose x. So now that we know this, we know that here we are going to have, since this is the probability yi given xi parameterized by theta, so this is going to be theta transpose xi. Because yi is 1 that we are focusing right now. That is why this is the positive distance. Yeah, so this is the positive distance that we are using, y 1 plus e to the power minus theta transpose xi. Why are we doing that? So basically what we have done is, if you remember di, we have written that as theta transpose xi. We don't want to get in this perpendicular thing, so we are just going to take theta transpose xi, and then which is kind of like removing all the constants yi. So yi equal 1 given xi parameterized by theta is 1 by 1 plus e to the power minus theta transpose xi, which is our distance, positive distance. Great. Now the next thing is, you can already guess what this is going to look like. 1 by 1 plus e to the power minus of minus theta transpose xi. So basically this is g of minus theta transpose xi. And this was g of theta transpose xi. Remember g, which is the sigmoid function, minus. So this is going to be 1 by 1 plus e to the power theta transpose xi. Great. So now we have this out of the way. It's very important to get the intuition for this, because once you understand this, 90% of the problem is done. So yeah, so we are 90% done. So now comes the gradient descent function, and how we are going to use this log likelihood function that we just now found out in order to find out the parameters, that is theta 1 and theta 2, that is theta basically, how we are going to use that. So we'll be using gradient descent, obviously. That is the only way here. So now we need to formalize that. So basically maximizing log likelihood is same as minimizing the loss function. So I hope you've seen the video when I've explained why this is the case, and I'll reiterate it. If you do not know this, then it's important to know this before you proceed. Okay, so I'm going to assume that you know this. So basically maximizing the log likelihood is the same as minimizing the loss function. So now we are going to write a function for the log likelihood. So what we had earlier was likelihood and of two distinct cases. Now we want to combine them together. So this combination, trying to understand this, is very, very, very important. I cannot stress it enough. Okay, so I'm going to use the formula directly here. It's not much. The previous page when I was discussing, it was the likelihood function. And now this is the log likelihood, just using a log. This is the function. Summation I equal 1 to m log of probability of yi given xi parameterized by theta. Great. So now we are going to break this down such that we can accommodate two cases. Listen very carefully. So this is the first one. So when y equal to 1, we want to take the case when y equal to 1 here. So basically our data set is divided into points such that y equal 1 and some have y equal 0 with some points x1 and x2. So we want to find out those points which have y equal 1 and take them here in the first part of the function. So how are we going to indicate that? We are going to use something called an indicator variable. So I is basically, so let me just go into this a little in detail. So basically, what is an indicator variable? So suppose you have a list of functions. Suppose you have y here. So 1, 1, 1, 0, 0. Let's say this is our y data set. And we're using this indicator variable. So if we do here 1 of yi equal 1, this means that whether y is equal to 1 or not. So this is true. So this will take the value 1. Here also it will take the value 1. Here also it will take the value of 1. Now here, is yi equal to 1? No. So this will take the value 0 and this will take the value 0. So do it with me. So if yi equal to 1, mention I equal 1, 2, there are 5 points. So then the answer would be what? 1 plus 1 plus 1 plus 0 plus 0, which is going to be 3. So this is the basic funda of indicator variable. So now that we know indicator variable, we can move on to the next part of this function. So what is going to look like? Now you can guess it. I think you can guess it. Yi equal to 0 given xi parameterized by theta. This would be indicator variable of yi equal to 0. Great. So whenever yi is 1, we are going to use this because probability of yi being 1 parameterized by theta given xi. And whenever yi is 0, we are going to use this. So now this log likelihood can be expressed like this very easily. Now the work is almost done. I can say it's 95% done. So now what we want to do is just put in this value. We know this value. So let me just clean this up. Okay, so now what we're going to do is do the substitution and then differentiate that and equate it to 0, right? Now we know this one. Probability of yi equal to 1 given xi parameterized by theta 1 by 1 plus e to the power minus theta transpose xi. I just now wrote it. And the other one is probability of yi equals 0 given xi parameterized by theta is 1 by 1 plus e to the power theta transpose xi. Okay, so now what we're going to do is substitute. So this function would look something like this. This would be yi by yi itself, because you saw that when I was showing that graph. So if yi is 1, then this will be 1, right? And if yi is 0, this will be 0. So we can just take yi. And then put in the function here, 1 by 1 plus e to the power minus theta transpose xi. And for this one, we know what is going to be. You can guess it. 1 minus yi. So if yi is 1, this will be 0, which is what we want. If yi is 0, this will be 1, which is exactly what we want. Perfect. So now we have 1 minus yi log of 1 by 1 plus e to the power theta transpose xi. Now we have this. Great. So now, as soon as we have this, our work is done. So it's now 100% done. So we just need to differentiate this and equate it to 0. And then we'll have an equation for our thetas. And we can just use that. We can use it like in gradient descent, as you know. So I'll just come to that. So first, let's simplify this before we differentiate. This minus is because I'm putting it here. And this would be, this would have a minus already. So we can just yi minus 1 log of 1 plus theta transpose. Cool. Yeah. So now let's remember this formula. Now that we have this formula, then let's differentiate that. Delta of ln theta equal to 0. I'm using delta again because we have multiple dimensions. Okay, so now we'll differentiate this one and equate it to 0. So let's differentiate. We have this equation. This is basically our LL theta at this moment, and we now want to differentiate this. So let's do that. So summation I equal 1 to m minus yi. We're differentiating with respect to theta. So this would get differentiated. So as we know, differentiation of log x. Differentiation, what is differentiation of log x? It's 1 upon x, right? So ddx of log x is 1 by x. So that is what we're trying to use here. And one more thing we're trying to use is ddx of f of x. Then it is going to be df dx upon x. This is going to go down, and then this will be df upon dx. So let's use that. So we put this down, and now we're going to differentiate this with respect to theta. Yeah, so with respect to theta, what would that look like? This would be 0, and this would be e to the power minus theta transpose xi, and this would be minus xi. Correct? Yeah, got it. So this one done. Now the next one. So what would this look like? Let's see. So yi minus 1 would be in that way. Keep that. Oh, it's the same thing. So the below it will go e to the power theta transpose xi, and here it will be theta transpose xi multiplied with xi. So this is the way it goes, and then we're differentiating this one. So e to the power x differentiation is e to the power x. If you know, ddx of e to the power x is e to the power x that we're trying to use here. So e to the power x differentiation would be this, and then differentiating this with respect to theta would be xi. Great. So we now have got both of these out of the way. This would get plus because of 2 minuses. Now, yeah, so now if you see, so this term and this term is similar. So we're going to club them together. Now, we are going to use a trick. Listen very carefully, otherwise you will miss it. Listen very carefully. I'm going to use a very simple trick, very old trick in the dictionary, but I'm going to use that. So if you see here, we have, what do we have? E to the power minus x, 1 plus e to the power minus x, right? So now, let's do that. So if I convert this 1 by e to the power x upon 1 plus 1 by e to the power x. Now get this up here. We would have 1 by e to the power minus x. We're multiplying with e to the power minus x. We are multiplying by e to the power x. So we would have e to the power x plus 1. Correct? These two are same. You agree? So now we are going to use the same thing with e to the power x. So e to the power x we have 1 plus e to the power x. So now we are going to do is 1 by e to the power minus x upon 1 by e to the power minus x plus 1. So now what will this be? Let's multiply by e to the power minus x. We would have 1 by 1 plus e to the power minus x. So does this look familiar? So now if we convert this one like this, we have the same denominator and we can combine these terms. Excellent, right? Remember this trick? This will come in handy later as well. Great. So now you just saw what I did. So I'm going to use that. I'm going to convert this one into this form. You will soon realize why I'm doing this one and not the opposite. yi e to the power minus theta transpose xi 1 plus e to the power minus theta transpose xi multiplied with xi. And this one, I equal 1 to m yi minus 1. Let's do this one. So what is this going to look like? 1 by 1 plus e to the power minus theta transpose xi. Correct? You got it? This is extremely a very neat trick that we use, and it solves most of the problems as you just saw. So now we have the same denominator. We can combine these two terms. So yeah, so let's do that. So let's simplify. So what do we have here? Let's see. We have 1 by 1 plus e to the power theta transpose xi. And here we have yi xi. From here, e to the power minus theta transpose xi. We have plus yi xi from here, and we have minus xi. So as you can see here, if you just take yi xi common, we have 1 plus e to the power minus theta transpose xi. Yes, we are very, very close to the formula that we want, the simplified form. So let's do that. Yi, xi, let's take that common. And we have 1 plus e to the power minus theta transpose xi upon 1 plus e to the power minus theta transpose xi. So these two get cancelled. And this is minus xi upon 1 plus e to the power minus theta transpose xi. We are nearing the term that we're trying to find, so do not forget this though. It's very important. This derivation is extremely important. It's gold, pure gold. So great. Now that we have this, so we are trying to find out. Yeah. We are almost. We are like literally at the end. So I'll just take this one out, put it here. So this is going to be, let's take xi out. So we are going to have yi minus 1 by 1 plus e to the power minus theta transpose xi multiplied with xi. So does this look same? Does this look familiar? This is what? This is the sigmoid function, correct? So let's put that in here. Yi minus g of theta transpose xi multiplied by xi summation I equal 1 to n. Perfect. This is the formula that we were looking for. Now that we have this, we know what delta theta, LL theta looks like, and we will just now use our gradient descent formula. So remember this formula, we have spent a lot of time and a lot of effort and hard work to get here. So this is very, very, very important. And if you've got this, then you practically understood classification. You have got it. Yeah. Perfect. Now let's do that. So now we are going to do the gradient descent. So if you know what is gradient descent, so basically gradient descent means, I'll just repeat it like in short. I have told about it. I've spoken about it in my earlier videos, but I'll just tell about it in short. So this is where we are starting. So this is our loss or our log likelihood that we are starting. Okay, so if we're not talking about log likelihood, then this would not be the curve in that case, because in log likelihood, we're trying to maximize it. In loss function, we're trying to minimize it. So the curve would look something like this. So here we are currently. This is our log likelihood. And we're trying to reach this point, which is our target, which is our maximum log likelihood function. So if you have this, so this is the target that we're trying to achieve. So what are we going to do? Simple. So we are going to use our gradient descent formula. Theta t plus 1. So we'll initialize theta with some random values or 0. And then we'll follow this curve. Yeah. So we're going to follow this curve. So theta t plus 1 is going to be theta t minus eta delta theta LL theta. Minus of this. So practically it's plus. Why is this? Now said we are going not in the direction of the slope, we are going to maximize the likelihood. That is why we need to move in this direction, which is very important. So now this is our gradient descent formula. So I'll just write it out again. If this is not very clear, plus theta, delta theta, delta theta. What you just need to do is just place the function that we just now derived in here, and you have it. And you can follow it for as many epochs as you want until you get convergence. This is the learning rate. And learning rate determines the rate of convergence. And we have theta at the end of this. Perfect. We've literally come this far, then you deserve a medal. You are a genius. You have understood everything and you can tackle any problem of classification now, be it in interview, in placement, in job, in GATE exam, in college exam, anything. Great, amazing. So now just a simple thing. So basically now that we have theta, we know that the equation of the line is going to be theta transpose x. If you remember that I was using earlier, theta transpose x, correct? So now it's very important to find out. So now we want to find out the equation of the line, right? So just remember one thing that we did. So when I was saying that our di is theta transpose xi, right? So, and g of di or g of theta transpose xi would be half if di is 0. Remember this, right? So let's get that from here. So 1 by 1 plus e to the power minus di is theta transpose xi. So I'm going to put this in here equal to half. Now solving the equation, what we have, theta transpose e to the power minus theta transpose xi, 1 plus is equal to 2. So this would be 1. So now theta transpose xi is equal to 0, which is exactly the equation of the line that we're looking for. And this will be the decision boundary. Remember this one that I was saying earlier? This is the decision boundary. The equation of this is theta transpose xi equal to 0. Perfect. Now we have got everything. Now given xi, we can easily find out where the line lies. And based on the line, we have the probability and we know on which side of the line it lies. If it's a positive one, then y equal to 1. The classified point is 1. And if it's on the negative side, it's going to be 0. Great. Amazing. Now we are done. Today we are going to discuss about a very important machine learning algorithm, which is SVM, or support vector machines. So this is a very powerful model which is used mainly in classification and in regression. And arguably it's one of the most important models out there in machine learning. So you should know this too. And if they ask you what is a common use case of SVM, so SVM is mostly used for small and medium sized data sets. Remember that. Okay, so let's first discuss the data set that is mostly used in SVM. So because data set is the most fundamental thing for all the machine learning algorithms. We are going to discuss classification first. That is why let's dive right in. Okay, so let's consider the data set. So this is an example of the data set. I hope the light isn't causing much problem here. But yeah, so this one will have y equal 1 and this one will have y equal 0. Right? This one will have y equal 1, this one will have y equal 0. So there are plenty, like millions of decision boundaries that can go right here, and that can be predicted by any kind of classification algorithm. All will be correct, all will have training accuracy 100%. Now let's see the problem with that. Let's consider a decision boundary. Let's consider a decision boundary that is done or predicted by any kind of common machine learning classification algorithms. So this is a decision boundary. As you can see, it has training accuracy of 100%. So you must think this is a perfect decision boundary. What is the problem with that? Okay, so now this decision boundary will not generalize to all new test cases. Why? Let's take an example. Suppose we have this as our test point. Suppose we have this as our test point. So you might be wondering, like, this is a very easy test point, right? It's clearly visible that this should have been y equal 1 because it's closest to this group of points. But because of this decision boundary, it will be classified as y equal 0, which is wrong, obviously. So that is why this decision boundary does not generalize well, even though it has training accuracy of 100%. So this is not correct. So which is the correct decision boundary that will be used in this case? Let's see. As you saw, this decision boundary is not correct. So now this decision boundary is the correct one. Why? Because as you can see, this generalizes perfectly. Why? Because you can see that the closest points, they are at equal distance from the line. So that is why any new points that you will have that are closer to either this group of points or this group of points, it will be classified perfectly. This is very important to understand. This is the decision boundary that will be predicted by SVM and it is the correct one. So this is the one that we are after. Okay, so now there's a different thing that we're going to discuss. So there are two kinds of classification that we have in case of SVM. One is a hard margin classification and one is soft margin classification. So what do we understand by that? So this one here, as you can see, it will have training accuracy 100%. It has decision boundaries that are capable of dividing the data points into y equal 1 and y equal 0 perfectly with training accuracy of 100%. It's possible because the data is linearly separable. There's no noise in the data. So this is an example of hard margin classification. So this decision boundary that we saw right here, this is a hard margin SVM classifier decision boundary. This is very important to understand. But you know, most of the real life cases, they will obviously have noise. Everything is noise. So that is why this noise will let, suppose for example, one y equals 0 point is right here. So it's impossible to classify the data perfectly in this case because this point is obviously wrong. It's wrong in the data set, but you won't know that because the data set obviously has noise. So that is why here in this case, we are going to ignore that example and we are going to take the rest of the examples that we have and we are going to classify and use this decision boundary only as our final answer.
Because suppose if we try to distinguish this and try to draw a decision boundary like this, so that this and this are separate, it's completely wrong. This will never ever generalize, and it's useless. That model is useless. It will just have 100% training accuracy and nothing else. Literally, no use. That is why soft margin classification is very, very important. So we are going to discuss hard margin classification first because it's very easy. And as soon as you understand hard margin classification perfectly, soft margin classification will be a piece of cake, just a little bit of change. Now that we are done, let's discuss the objective function for this, the mathematics behind this. It's very easy, I promise you. You will be able to understand it like very easily. Okay, so now let's discuss the objective. You remember, I just now said this distance is the thing that is the most important in SVM. So this is the distance that we are going to formalize. So this is basic coordinate geometry. If you don't know this, like this is the most basic equation of the coordinate geometry, I would encourage you to revise the basics a little bit. W transpose xi. So this is the distance that we have right here. This distance we are going to try to maximize. For which points? Not obviously for all the points. So here, the closest points to the line or the plane are the most important. What we are going to try to do here is that maximize the margin. So maximize the distance of the points that are closest to the line or the plane. What is margin? Margin is the distance of the points that are closest to the plane. So it is the minimum distance of all the points that are in our data set, right? So that is why this distance is the maximizing the margin. So our objective is to maximize the margin or maximize the minimum distance of all the points in our data set to the plane. This is very important to understand. We're talking about hard margin here. So one more thing is very important. Let's formalize that using TI. So TI. So one thing is very important, TI. So what is TI? TI is basically positive for all the points that are in the positive training example, that is y equal 1, and it is negative for all the training examples that have y equal 0. This is used because we know that this is hard margin classification and we're going to use that to our advantage. So TI we have formalized, we have DI, now we are going to use it to form the equation. One more thing before we do that, if you understand it carefully, so we are trying to maximize DI, where DI is the margin. Margin is the distance of the closest points to the plane in our data set. You got it? So this is the closest point here, this is the closest point here. So the margin is this distance and this distance. So we are trying to maximize the margin. You understand that? Obviously, if we maximize both of these, then we have the perfect decision boundary. You see? It's very, very simple and it's very, very intuitive as well. So great. So now we're going to try to write the optimization function. So once again, I'll go over it. So DI we're trying to maximize, so which means we are going to minimize this mod W. So here's a very cool thing that we are going to see now. Let's keep this for now. So we are going to try to minimize this mod W. So one more thing is very important here. So mod W square is going to be W transpose W. I hope you know this. Mod W square, this is basic vector. Mod W square is W transpose W. So we are going to use W transpose W here. Why? Because W mod is not differentiable at 0. That is why we are not able to use that. This is a very common thing in machine learning and in derivations as well. We won't use the function that is not differentiable. It complicates things unnecessarily. So we are going to use W transpose W. So our objective function will be y half. Y half because W transpose W is mod W square. So when we differentiate this, we'll have a 2 and the 2 will get cancelled and we'll have mod W. That is why this half is very important. Yeah, subject to the constraints are very important in any kind of optimization function. TI, you know TI I just now mentioned. This is the function that you should know. This is the optimization function. Minimize half of W transpose W subject to TI. You know TI, which is positive for all the y equal 1 and negative for all the y equal 0. TI, W transpose xi plus b greater than equal to 1. You know why? Obviously, because this one is 1 for positive points, this one is -1 for negative points. So this should be greater than equal to 1. Very, very important. Great. Now we have everything we need. Now you plug this into any kind of optimization software. You can use Gurobi if you want. And I always use Gurobi. I used it in my BTech project as well. So yeah, that's a very cool software that you can use too. Great. Now a very fun fact or a popular interview question, as you call it, is incoming. So basically, why is it called SVM or support vector machines? We did not see either support or vector or machine, anything. So basically, these points which are the closest to the line. So these points which are the closest to the line, these are called the support vectors. And they are the most important. They are the only things that matter in SVM. So that is why these points are called support vectors and this is called support vector machine. Okay, so we are going to discuss an extremely important ML algorithm, which is decision trees. So the name itself suggests the kind of algorithm and the kind of data set that we are going to deal with here, right? So the decision tree is actually arguably the most powerful ML algorithm that is out there that can fit a complex data set. And also it is like very important for your ML career and understanding. So you have to listen carefully. And if you follow this video till the end, I can guarantee that you will be able to understand all decision tree questions. You will be able to solve all of them in college, exam, in GATE exam, everywhere, in interviews, and you will be able to master this concept perfectly. So what do we mean by hypothesis space? It is the sample space of all the data points that we are going to use in this model. And so our hypothesis space here in this case is going to be a tree. Big deal. So, okay, so now that we have this, let's take and let's consider a sample data set to understand the concept more clearly and more thoroughly. Okay, so so what we are going to do here is that we are going to consider a data set of flowers, and there's going to be 3 kinds of flowers and they are going to be decided based on like 2 features. We are going to keep it very simple so that you understand the basic idea. So there are 2 features that we are going to consider. One is petal length and petal width. And based on these 2 features, we are going to divide our data set into 3 classes. Okay. Let me show what I'm trying to say. So suppose this is our first node. Total sample points that we have is 150. That is the total number of data points in our data set in the beginning. At the current moment, the total points is 150. So this is the first node in our tree. So you know, like a tree, what it looks like. This is a tree, right? So this is our first node in this tree, arguably this node. So we have total samples as 150. So now this one would have petal length, let's say that is less than equal to 5 centimeter. So what do we mean by that? So we are going to have, like, let's say the total length in our data set, petal length, it varies from 0.5 centimeter to 10 centimeter. So 5 would be an appropriate middle ground. So let's say around 50 points have petal length less than 5 centimeters. So that is going to be yes. So this is the question that we ask at this node. Is the petal length less than equal to 5 centimeter? Yes. Then we go here. This means that this has sample data points 50, let's say. And the class, like whenever the petal length is less than equal 5 centimeter, we don't need any other features. We can directly say the class is going to be x1. Here, all the points, 50 points, they have class x1. So remember, this is not the real life. This is basically a sample scenario, a very dumbed down scenario that I'm using so that you get the basic point of decision trees. So this is the, at first node, you ask a question. Is the petal length less than equal 5 centimeter? Yes. Then you go here and you have total 50 samples out of 150. So the rest 100 samples have petal length, which is greater than 5 centimeters. This says class x1, some class. Now let's say no. So we know now this has 100 samples. So now, and 100 samples, and we have 2 classes here. Some are x2, some are x3. Based on this x1 class, x2 class, and x3 class. So basically here we would have, let's say, now the next question we are going to ask here, because we have not reached a single class at this node. So next question we are going to ask is this less than equal 5 centimeter? So we know the sample here, total samples is 100. Great. So now that we are going to ask this question here, this is going to be yes for some and no for the rest. So this is going to be again a leaf node because now we have class x2 only equal to x2. So this one, let's say this has 45 samples. So 45 total samples in our dataset has class equal x2 and it has petal length less than 5 centimeter. Sorry, petal width less than 5 centimeter and petal length greater than 5 centimeter. We have this. We have 50 samples in our dataset of class x1 having petal length less than 5 centimeter and some wide variation of petal width which we don't care. Because petal length less than 5 centimeter means 50 class samples from our dataset that our model will learn. And no. Well, how many are left? 55. So this is going to have 55 samples. This is 55. And class is going to be x3. Right? So this is class is going to be x3. Samples total is 100. Total 45 samples here, 55 samples here. And we have now got ourselves a decision tree proper implementation. Okay, so let's get acquainted with some terminology. So these three, this, and this. These three are the leaf nodes. What are they? These are the leaf nodes. A little bit of cursive. These are the leaf nodes and these are the internal nodes. These are the internal nodes. So at each internal node, we split based on a particular attribute or a particular feature. And at leaf nodes, we classify it as a particular class and it is where our tree ends. Now, this is basically at training time, how we make our tree. So now the question is, what do we do at test time? Suppose we have a particular X here, as in we have a particular petal length, we have a particular petal width. Now, what do we want to do? We want to find out which class it belongs to. It's very simple. I think you can all guess it. It's OH only. Yeah, sorry. So basically, you can use this to think about it. So OH, H is the height of the tree. So at each node, we know whether it's yes or no. So we don't need to explore the entire tree. We will go down perfectly the height of the tree and then we'll be able to reach either of the leaf node. So let's say we have something like a petal length is 2.5 centimeters. So then yes, and we have class x1. The petal length is let's say 5.5 centimeters and we know it's going to be no. Then we are going to ask ourselves, we have it in the data set, petal width is 2.5 centimeters. Then we know it's going to be x2. If petal width is 5.5 centimeter, we know it's going to be x3. Very simple, easy peasy. Okay, so now that we have this, let's try to dig a little deeper. Okay, so this is a very, very easy example, but let's try to take another example and we'll try to bring out the maths based on that example. Okay, so now that was a very, very basic example. Let's take another example to understand it very clearly, even more clearly. So let's classify based on like humidity and precipitation. We will also see the graphs here. So focus carefully. So this one is humidity. So now you know less than 50% or greater than 50%. So if it's less than 50%, question mark. So that means, let's say yes. So it means it's not that much humid. So it's going to be sunny. The class is sunny. We can also write this class, denote this class as 0. Okay, let's go with that. Now you know, so I'm going a little bit faster here. So no means the next feature will come here. Precipitation. Is it less than 50%? Okay, the handwriting is going a bit bad. So yeah, I mean, you can understand this. This precipitation less than 50%. So this is going to be, let's say yes. Then what do we have here? Humidity less than 50%. Precipitation also less than 50%. So means cloudy. Let's say this class is 1. We are denoting the class as 1. And now let's say no, which means it's going to be rainy. Which means this is higher than 50% precipitation, greater than 50% humidity. Okay, so one thing I mentioned. So this cloudy means greater than 50% humidity, less than 50% precipitation, going to be cloudy. If it's greater than 50% humidity, but greater than 50% precipitation, it means rainy. So we are denoting this class as 2. This is another simple example. I hope you get this. This is very easy to understand. Now that we are done with this, so now basically these classes 0, 1 and 2, these are like our y or the target variable, right? So we don't generally represent this as 0, 1 and 2. Instead, we use our binary representation. So it's called one-hot encoding. So what do I mean by that? So basically 0 would be represented as 0, 0. 1 would be represented as 0, 1. 2 would be represented as 1, 0. So where am I getting this? This is the binary representation that we are using. And this is the one-hot encoding that we will be using in our code to implement this, because it basically standardizes the things and it's easier to handle. Now, how did 2 get transformed into 10? So this is basically the binary representation. This is like very basic of CS. I think you know this, but still I'll just go over in brief, like in 2 to 3 seconds. So basically how we are getting this to this. So basically in binary, we have the base as 2. In decimal, this is decimal. In decimal, we have the base as 10. So when you want to transform decimal into binary, so what we're going to do is we're going to divide 2 with 2 because of the base. So it's going to be the remainder. This is 1 and the remainder is going to be 0. Again, we divide 2 and we get the remainder as 1. So basically, this is how it goes. 1, 0 is our final answer. So regardless of whatever it is, basically you take the remainders together in the reverse order and then you have the binary representation. This is the binary representation or the one-hot encoding that we are talking about here. One-hot encoding. Let me just write that down. One-hot encoding. Great. So now we have this out of the way. Now I also want to discuss another important thing. Keeping in mind this graph. So basically these, as you know, I said these are the leaf nodes. Now it can happen, remember this very carefully, it can happen that even though humidity is less than 50%, still some point here is there that is like cloudy. It can happen, right? Humidity less than 50% doesn't always mean it's going to be sunny. So let's say this has total 49 samples and one sample is of cloudy here. So this one has one sample cloudy and 49 samples of sunny. So in this case, what we are going to do is that if we know that this is our final tree and we do not want to divide this any further, so then we know that this node is going to be sunny. So there is a very slight chance of this being cloudy when we are trying to, at the test time, when we are trying to decipher a particular point. So, but whenever we are classifying this node and we know that this is our leaf node, we are going to take the number of the class name of the one which has the larger number of samples. So this one we are going to classify it as sunny. We won't bother about cloudy at all unless we want to divide this further. So this is going to be sunny. Great. So now that we have this, it can happen. Like it is not necessary that all the points here will be of sunny. It can happen that it can have one as cloudy. So now that we have this, let's try to draw a graph to understand this even better. Cool. So now let's draw the graph. So we have only two features, so we can use a 2D graph here. So this is going to be, let's say this is precipitation and this is going to be humidity. So we have the first one, if you remember, it was humidity less than 50%. So this one, let's say, is 50% for humidity. This one is 50% for precipitation, right? So this one is 50%. So if humidity is less than 50%, regardless of precipitation, this entire thing is sunny or class 0, right? So this is very easy to understand. Less than 50% humidity, this line, this entire thing is sunny. Great. Now when humidity is greater than 50%, then precipitation comes into play. So this one, let me just remove this because this is not needed. This one is not needed. So we only need here this line. So if humidity is greater than 50%, and precipitation is basically less than 50%. So this region, let's just draw this here. So what is this region? This region is going to be, this region is going to be cloudy. This class 1. And this region, just to denote them separately, this region is going to be rainy. So our class 2. Right? So we have humidity. We have humidity and precipitation as two features. We have sunny, we have cloudy, we have rainy. So this and this, these are the decision boundaries that we are trying to find in our data set, in our model. Like, you know, in classification, we have decision boundaries. So similarly, in here, in decision trees, we have these decision boundaries that we are trying to find. Okay, so there's now a fun fact time. So basically, decision trees do not require any kind of data preparation or any kind of feature scaling, nothing. It's very easy and very simple to use. So, I mean, this can be a popular interview problem. So remember that. It's very important. Remember this, but it's also a fun fact. Okay, so now that we know our target variable and the data set properly, and we have a good idea of what we're trying to solve, now the next thing that comes is how we can get the attribute we need to split at each step. So as you remember, first in my example was humidity, then it was precipitation. So that was just a random example, but we need to know which attribute. Suppose we have a lot of features and we need to know which feature we want to use at each step, right? That is very important. So now that, so we obviously can't have like a huge tree with like lots and lots of features, and like suppose we had used precipitation earlier, then we would have gotten a larger tree. We need to find the most optimal and the most shortest tree that we can use, and that would make our process faster. So that is why we are now going to understand the maths behind how we are going to decide which attribute to split at each step. Okay, so let's get into that. It's going to be a little involved. I'm warning you, so be very careful and listen carefully. Okay, so now we know that y is going to be our target variable. So y takes values from 0 to r minus 1. So when we have r total classes. In our example, r was 3. So now the formula that we are going to use here is this. So let's say like we have probability of y equal y. So what do I mean by this? So y is our target variable that we are using here. So y takes values from 0 to r minus 1, as I said. R minus 1 when we have total r classes. In our example, r was 3. So this is going to be the probability of how, our y variable is distributed over this. Now that we have this, so now we know this. So now the next thing that comes is h of y. So this is a very important term that we are going to use. This is entropy. Why we are doing that, I'll get to it in a bit. So h of y is probability of y equal y, this term that I just now mentioned. Now, very careful, listen. Log of probability of y equal y. So what is this? This is the surprise associated with all the data points. So why do we use this to represent the surprise? Because suppose if we had only one class, that is class 0, then probability y equals 0 would have been 1. So in that case, log of 1 would have been 0, which means there's no surprise. All the classes are 1, so we don't have any surprise. And log of this thing, it represents the number of bits that we are using in our representation. So that is why log is very important here. Let's try to see it in a different light so that we understand it better. This. Okay, so now we can also think of this in a different way. This is expectation of minus of log of probability y equal y. So expected value, this is basically our entropy is expected surprise. Why? Because you know this will be if we basically do this. Okay, one thing I forgot, summation over y. So this one would be summation over y, probability of y multiplied by the term. Log of p of y equal y. So this is our entropy that we have here. This entropy is basically the term that we are going to use to determine which attribute we are going to split at each step. So why are we going to use this? Let me try to explain that. So entropy means the randomness or the chaos in a particular system. As you know, like Brownian motion, it was like full of very chaotic. So similar is here as well. So basically Hy represents the entropy, which is the randomness. And we want our system to have zero entropy. We always want that. We always want a stable system. So that is why whenever in a particular node, now listen very carefully. So you remember this one was our decision tree as it was going. So this was the leaf node. In a leaf node, I said, if you remember, I said that there could be that some small percentage of points that are of a different class, right? So we want this node to have all the classes of a single class variable, all the data points to have a single class here, right? Then we know for certain that whenever this attribute is going to be satisfied and we come to this node, we know that this node is going to be of that class with 100% certainty. 100% certainty means this set has entropy 0. Remember this. So basically what we want here is to minimize this entropy. But this has no x, that is no feature, so we don't know how to do this. So now comes in the conditional entropy based on the feature. It's interesting, right? It's getting interesting. Yeah, so now comes the conditional entropy based on the x, so which we'll use to determine our the feature that we are going to use to split at each step so that we get to a tree that has the least entropy and is the most stable. It's very interesting. Please listen carefully. H of y given x. X is our feature. This is going to be simple. Y equal y given x equal x minus log of probability of y equal y given x equal x. Summation y. Perfect. So this is the conditional entropy. Conditional entropy. This is our conditional entropy that we are going to use always to determine which x to use at each step to split at each step. So this one we used humility. So in this node we are going to apply this formula h of y given x. X we are going to take in all the xj's. So here we had two x. So basically it was humidity and precipitation. We would use humidity and try to find this out, and we would calculate this formula, this value. We would use the next one, which is our precipitation, and calculate this. Whichever has the minimum h, we are going to use that to classify based on our, we are going to use in that node to split the tree. Perfect. I think you get this. So this is very, very, very important. Now that we know this, our work is done. Practically done. It's not even 95% or 98%, it's 100% done. So now it's time to write a short pseudocode so that you understand what I'm trying to say. And you can implement that in any language that you prefer. And you can try it out to see that it works. I can guarantee you it works. I'll also make a video showing the hands-on implementation. But if you want to do it right now, I'll share the pseudocode. Great. So now I'll share the pseudocode. So first thing is D, which is our data set. Xi, comma, yi, I equal 1 to m. Let's say we have m total data points. So this is our data set. Now let's say our class, our function name is learn tree D. So first thing, as you know, if we are writing a pseudocode, we'll have to get the edge cases out of the way. It's kind of a recursive one. Our tree is obviously recursive. So first thing, we need to get the edges out of the way, edge cases. If we have xi, comma yi belongs to D and yi equal to k. So for all I. So for all I, if we have at this node, whatever I we have, so for all I, it belongs to the data set, obviously. That's the known criteria. It belongs to our hypothesis space, as I said. And yi is k. That is, all of them belong to the same class. So now we know that this is an edge. So this is going to be a leaf node. So we know this is going to be a leaf node. So return new leaf. Okay. This is an edge case that we have. Get this out of the way. Now the next thing is xj. So basically xj, choose xj. How we are going to choose xj? Don't write choose in pseudocode, but xj is going to be such that minimum of h of y given x among all the features. As I just now said, the minimum entropy we are going to use to choose the xj. Now we have the rest of the tree. So the tree would be d of. Now we know the tree would be d of L such that it will have all those points xi comma yi such that xi is S. So just now shows j. So this j is going to be this L that we are going to use here, and dl is our new tree. Let's give a comma here. This is going to be our new tree with the remaining with the attribute that we chose to split, and this is our tree. Okay, so now that we have done this, we know the tree that we are going to use based on the particular feature that we are going to split our tree. So basically now we are going to return. We're going to return based on the attribute that we just now decided and the rest of the tree. Perfect. Now we have this out of our way. This is just like recursive function. Base idea, I think you have got it. And it's very important to understand this so that you can implement this on your own very, very easily. And whenever you're using any kind of scikit-learn library as well, you know which hyperparameters to use. We know which loss we are using. This loss is very important, like very, very important. It's an extremely popular interview question. Cool. Fun fact time. So decision tree is actually a white box model because it's very easy to understand and we know exactly what is going in it. We can implement it from scratch. But in often other cases that, like, for example, I'm not going to mention the example. Think of that, which are the black box models that we don't know what is going inside. We just know the input. We don't know what's going inside, what formula, what recipe it's cooking up. And we just know the output, and we can change some parameters, true, but we don't know exactly what is going inside. It's not very intuitive. So think of such examples and then drop them in the comments. I'll check and see whether you're right or not. That's very, very important. Today we are going to discuss one of the most important machine learning topics, which is dimensionality reduction. We're going to look into some common algorithms, which are like principal component analysis or PCA, and we're going to learn how and why we do this dimensionality reduction. And we're going to take some examples and show you the math. Let's break down the math so that you can understand the coding and you can understand the math and derivations easily. Great. So now that we have that out of the way, without any kind of further ado, let's start. So many kind of machine learning datasets that we have, that we see in our real life, they all have millions and thousands and hundreds of examples of features. Not like the normal house prediction ones, the ones that are like very complex. For example, stock prices, which keep on changing at any point of time. So many HFTs are just fighting to get the best benefits and the best profits. So these all have millions of features, obviously. So often in this case, the training becomes very, very slow and inefficient. So what can we do to reduce the dimensionality when we have such a large data set? We can't just remove some of the features randomly. We need to have a proper direction. So that is where the dimensionality reduction comes into play. For example, let's consider the MNIST dataset. We know that it has so many handwritten images, like digits that we generally see, and we try to classify them, right? So these MNIST dataset that we have, it also has so many features. But now if you think carefully, very, very carefully, the ones that are on the borders, as you can see right here, the ones on the borders, these are all white. So we can as well remove them easily, and still we would have so much dimensionality left, and the accuracy would not be affected much, right? So that is why here we can try to optimize our training and make it faster and reduce 70% of the dataset if we just remove the white borders of most of these images. Also, some of the images where the black borders are very, very close together, we can actually not consider one separately, we can take them as a single one. So these are some of the optimizations. If we are done properly and through a proper route, you can actually get great benefits. And also, this is obviously, since it's so important, it's also a very favorite topic of the interviews. So let's focus on this now that we know why we're trying to do this. Okay, so now why would dimensional reduction work in general cases? So mostly when we are dealing with a very high dimensional space, so most of these training instances, they are not actually uniformly distributed across the entire space, because I mean, consider a very high dimension. So then there's so much space. Obviously, we don't have the training instances distributed exactly thoroughly across all the spaces. It is very practical to think that they will be congregated in one place. So that is why this has been observed like over statistics of many examples. So that is why we are going to use that to our benefit. What we are going to do is we are going to map that down to a very lesser dimensional subspace and still capture most of the variance of the data. Let's take an example. As you can see right here, we have an example of so many points that are actually, if you look very, very carefully, you can actually see that they are very closely linked to a 2D plane. So if you can see that this is actually a 3D space, right? But the points are distributed such that they appear to be lying very near to a plane. So that plane we can actually deal with, and we'll get like a very high accuracy, like whatever was achievable in the 3D space. Not exactly that, but very close to that. And still, our training will be so much faster and so much easier. Exactly, we have now just reduced our 3D dataset to a 2D one and still capturing all the values. One more very cool example is the Swiss roll. So as you can see right here, this is an example of a Swiss roll dataset. So if we project it directly, then you will see that the dataset is not exactly capturing the entire variance. But if you unroll it, see like this, and then you are able to project it down here like this, so then you actually have a very good dataset, and it's all in a plane. You have converted from 3D to 2D successfully. So this is very important as well. Now we're going to discuss the PCA, which is the principal component analysis. What does it mean? The principal component is the one that we're trying to find. So what is this principal component? It's actually the axis. Remember this, it's actually the axis of the dataset where we have captured the maximum variance. For example, let's consider this. This dataset, as you can see right here, there are three different kinds of axes that we can take the data against, right? So this dataset has this axis on which it has the maximum variance. So that is our first component or the principal component. The next one is the second dataset, along which it does not have much variance captured. And the last one is very little variance captured. So obviously the one which has the largest variance captures the most features about the data in 2D space when we are converting from 3D. So that is why we are going to use that. Very simple logic, right? You're with me so far? Very good. So this axis is also called as the first component, as I said. Why? As there is another definition for this axis as well. The one that is having the minimum difference between the variance of the original variance in the dataset and the final variance when it's projected onto that axis. So that is the mathematical definition and the one that we are going to use. Now, after we have found out the first principal component, our work is 95% done. Now what we are going to do is we are going to take the one axis which is orthogonal to this one, and we are going to get the variance along that axis as well. So let me try to break it down. So we have a 3D data set, right? So now this axis is the one along which we have the max variance. So that's the first component. Now we are going to take the one that is orthogonal to this, which is this axis, and we're going to take the variance of that axis. So now we have two axes compared to the three axes that was earlier, and these two axes capture the most amount of variance. Get my point? So from 3D to 2D, we're coming back. So like this, whenever we are coming from n-dimensional space to suppose we're coming to d-dimensional space, so d could be n-3, could be n-5, could be n by 2, whatever it is, we are going to go step by step. We are going to take the axis one by one. The one along which there's the most variance, then the one along which we have second highest variance, which is orthogonal. That is also very important, not like any axis. Which has the second amount of variance, again orthogonal to that, which has the third highest variance, and so on and so forth till we get the d dimensions that we are looking for. This is just the very crux of the intuition behind dimensionality reduction, and there you have it. It's very, very simple. Now let's draw that on pen and paper. So we are going to use here a standard matrix factorization technique, which is called singular value decomposition, or SVD. So as you can see right here, this is the formula for SVD, and this V contains the unit vectors that define all the principal components that we're looking for. See, it's very, very easy. You can just put it into any kind of software, and the software will give you the V. We'll see as soon as possible in this video only. So stay tuned. Do not Do not go away. So this is what the SVD matrix looks like. One more thing which is very important, as we will see right here, is that the PCA requires the data to be centered around the origin. So if you're using a PCA from scikit-learn, then you don't need that. But if you're doing it manually from scratch, then you need that. For example, as we'll see right here, this is the piece of code that you need to remember. Write it down, note it down, and use it next time. I'll show one example that we'll soon do here. Some face image segmentation that we're going to do using PCA. So stay tuned. MNIST dataset also we can use PCA there. I'll show you that as well. We'll come to that. And after this is done, the way you will get we have the vectors. Now we just need the dataset. Final dataset, that is a reduced dimensionality dataset. So this is the formula for that. And very simple, this projection. And we already have the vectors. So it's just a piece of cake. And yeah, there you have it. You have the dataset finally. So we'll do that on MNIST dataset and it will actually reduce it by 70%, which is a huge benefit. There you go. We have covered the PCA in its entirety. Some of the examples, some of the extensions of PCA we'll soon cover. For example, randomized PCA, kernel PCA. But till then, all the best. This is what is needed for your ML roadmap. And yeah, you have it. You've covered it. You deserve a round of applause. I'm really proud of you. Let's go. We'll see you in the next video. Till then, take care. Bye-bye.